Today's video is about measurement decisions, not statistical tricks, not models, but the choices made before data collection. Think of this as an architecture, a structure of decisions that determines whether your conclusions will hold or collapse. Most research does not fail in complex analysis. It fails at the very beginning. Most bad statistics are born from one wrong decision, choosing the wrong thing to measure. If you measure the wrong construct, no analysis can fix it. Good measurement is not accidental. It is a sequence of 4 deliberate choices. First, define the relationship you want to test. Second, classify your data correctly. Third, acknowledge that all measurement is imperfect. Fourth, certify the quality of your measurement. If these are done well, analysis becomes straightforward. Every hypothesis is a statement about a relationship between variables. The first task is precision. Which variables are involved and what roles do they play? Are you testing causation or are you testing association? That distinction determines everything that follows. A variable is anything that can change across people, places, or time. A hypothesis connects at least 2 variables, a proposed cause and a proposed outcome. To test a scientific claim, you must measure both ends of this relationship, not just the outcome and not a vague proxy for the cause. The language you use signals the strength of your claim. If you directly manipulate a cause, you should speak of independent and dependent variables. That language supports causal inference. If you observe variables as they naturally occur, you should use predictor and outcome. This protects you from causal overreach. Same mathematics, very different claims. Correlation is not causation. The second decision you need to make is about classifying your data. Not all numbers are created equal. How a variable is measured, its level of measurement, determines which mathematical operations and statistical analyses are valid. Misclassification here guarantees problems later. Some measurement is about sorting into categories. Binary and nominal variables place observations into groups with no intrinsic order. Coding categories with numbers does not make them quantitative. The numbers are labels. Ordinal variables add order, but not equal spacing. Ordinal data tell you who is higher, not how much higher. Other measurement places values on a continuous scale. Interval scales have equal spacing but no true zero, so ratios are meaningless. Ratio scales include a meaningful zero, making ratios interpretable. A key distinction is between discrete and continuous variables. Some variables are recorded in steps but represent continuous processes, while true counts are inherently discrete. Treating counts as fully continuous can produce nonsensical interpretations. Consider these examples. Pain rated from 1 to 10 is typically treated as ordinal. Higher means more pain, but the spacing is uncertain. Reaction time in milliseconds is ratio. 0 means no time elapsed, and ratios are meaningful. Jersey numbers used as codes are nominal labels. Averaging them is meaningless. Focus on the reasoning, not just the label. Decision 3 is about how you handle measurement errors. No measurement is perfect. The difference between the true value and what you record is measurement error. Understanding where error can enter your study is the first step toward reducing its impact. Every observation combines signal and noise. Observed value equals true value plus measurement error. Error arises from systematic differences in conditions and from differences in measurement methods. Direct measures use standardized units and reduce ambiguity. Indirect measures rely on proxies and are more vulnerable to error. Indirect does not mean bad, but it requires stronger design and validation. Finally, you need to decide how you assure the quality of your measurements. Before you trust results, you must trust your tools. Measurement quality rests on 2 pillars, reliability and validity. If either is weak, your conclusions are fragile regardless of sample size. Validity asks whether you are measuring what you claim to measure. Reliability asks whether the measurement is consistent under comparable conditions. Reliability is necessary for validity. An inconsistent tool cannot be a valid measure of a specific construct. If the construct itself truly changes over time, lower test-retest reliability may reflect reality rather than a flawed instrument. Let's do a quick recap. Before collecting data, force yourself to answer 4 questions. What is my predictor and my outcome, and am I manipulating or observing? What is the level of measurement for each variable, and what analysis are therefore valid? Where can measurement error creep in, and how will I reduce it? What evidence supports reliability and validity? Are my measurements tools consistent, and how do I know they measure what I think they do? If you answer these up front, Analysis becomes explanation, not rescue. Thank you for watching this video. If you enjoyed this lesson, make sure to like this video and subscribe to our channel. See you next time.